And we're back. Last couple of times, we looked at plane waves in very simple materials. We solved Maxwell's equations for an important case. And that case was a construction of a plane wave, which had a particular polarization. I think we solved it for the x direction of polarization. And we propagated it in the z direction. And we saw that as a function of time and as a function of z, we had sinusoidal solutions. Sinusoidal solutions. The plane part of the plane wave was that I did not let my x-polarized electric field vary in the xy directions. So if the z is out towards you guys, then the x will point up. Then the xy plane at any instant of time and z is a constant. Forever and ever and ever and ever. And furthermore, what we found was pure sinusoidal solutions, so that if I moved 10 meters ahead and I stayed at that spot, I would float up and down on exactly the same wave as if I was a quark or an electron at z equals 0. Okay? The electric field behaves that way. We substituted that electric field back into Maxwell's equations, and we solved for the magnetic fields. And finally, we did E cross H and solved for the Poynting vector. And we saw something very important, that the electric field was perpendicular to the magnetic field, was perpendicular to the Poynting vector where the propagation of the energy went. Okay? And that's something that's quite general and quite useful in figuring out Maxwell's wave equation solutions in a lot of other scenarios as well. Okay? So I want to go back and I want to do the same thing, but now what I'd like to do is I'd like to look at a lossy material. Okay? So this will be a boring review for most of you, with just enough of a twist to maybe keep some of your attention, maybe keep your eyes open for a little bit longer than just sheer boring repetition of what we had before. Okay, well, we'll see. If not, then I'll throw stuff at you to keep you awake. So we're talking about materials, and the constitutive relations, or the material relations that we're going to look at, is the simple relationship between D and E. And I like to say that this gives rise to some sort of capacitance in our system. And I say that mostly just out of the deference to the units of measure of epsilon, which is farads per meter. B related to H through the permeability, mu, which I like to say brings the inductance into the problems. And again, that's because the units of mu in MKS systems are henries per meter. Okay. And then we have a third constitutive relation, which is J is equal to sigma E. Okay. And what I like to do is I like to use sigma. Well, first of all, sigma, if I take it literally, if I take sigma literally, it's a metal. Okay, it's a metal surface somewhere in there, or some suspension of metal particles. Conductivity may be viewed as a literal term. That current, this is literally Ohm's law. V equals IR. Okay, the units of sigma are mhos. 1 over mhos are ohms. So if I bring sigma to the other side, I have V equals IR. That's a literal interpretation of this material relation. Okay? If I think about what a finite conductivity means, however, it means that I not only have a conductor, but by its nature I have a resistor. And if I have a resistor, then I have something that I can heat up and make toast out of. Okay? So it's a loss term. So if I have a resistor, the voltage drop across that resistor is going to take energy out of the electromagnetic system and put it into the material system as heat. It's no longer part of the electromagnetics of the problem. It's really just good enough for boiling water or toasting bread. Okay? It's not. So therefore, I can generalize and I can say every time I see a conductivity, I can use that to indicate a loss of energy out of the electromagnetics of the system and into another mode, another type of energy, usually heat. Okay? So I'm going to look at sigma as a general measure of loss. And that holds great that holds exactly right if it's the literal metal interpretation. But I want to expand that interpretation a bit to include any old loss that robs energy out of the electromagnetics of the situation and puts it into let's just say heat. Keep it bounded. Okay. I have Maxwell's equations. And we manipulate Maxwell's equations to turn the information into these are all first order partial differential equations. We want to turn these into second order partial differential equations that are not coupled. Okay, so these are first order set of coupled differential equations. And basically what we do is we take the curl of one of these guys here. That gives us the curl of a magnetic field here. We pick up the curl of the magnetic field here and shove it into there, taking into account the material constants. And things fall right out. So I'll sketch it here. And that guy there now will become a sigma E as well. Oh, and then this D here will be epsilon E. So this D will require this material relation, this J will require this material relation, and this whole term in H will require this material relation to substitute back in. Okay? Let me write that out a lot more neatly for you guys. Okay? But I think it's useful to see everything together. And besides, we did mostly this last time. So taking the curl of both sides means that I have a curl of B in there. Rewriting B in terms of mu, H gets me an E and an H together. Substituting in for the curl of H gives me a second derivative with respect to time of my electric field, and it also gives me this J term here. I'm going to use the constitutive relationship, sigma E, to turn this term into a first derivative with respect to the electric field. This term here if I take a look at this guy is an epsilon E. Pull the epsilon through, divide by that epsilon, and I have the divergence of E is equal to rho upon epsilon. And now if I have a constant charge distribution or a zero charge distribution, that term goes to zero. Okay? So last time I spent an entire, or the time before that I spent an entire lecture getting from here to here. Now I'm purposefully doing it much quicker, just so you can see the flow of it, just see how easy it is. The only thing I've done differently is I've kept this term here. Before, we only had those two terms, and now I have an additional first derivative term. And I've told you that in general, first derivative terms give me losses. And I know in this particular case, this first derivative term gives me losses because I've already told you how I'm going to interpret that sigma. Okay, it's more than just a lossy metal. It's any kind of thing that robs information out of the robs energy out of the electromagnetics and puts it into heat. Okay? I'm very sloppy here, I apologize. Each of those are vectors. So this is a vector wave equation. So if E is equal to EXA of x, and if I'm going to look for the same plane wave solution that I had before, then I have a scalar wave equation . And let me double check my minus signs. This should be a plus, right? People agree with that? So this is a scalar wave equation.
Is your loss term first derivative or second derivative?
First derivative, thank you very much. Has to be a first derivative. Stokes' law of drag. So now if I put this guy in here, the Laplacian of the scalar gets easier. And I have that. Now we had so much fun last time. Substituting that term into there, our complex exponential. And we know already that that guess solves that equation. So I might as well try to solve that equation there. Now, this is not a completely preposterous guess. It's not a completely ridiculous idea, because I talked about last time that the substitution of this into the equation is the same thing as Fourier transforming that equation. This is linear differential equations, constant coefficients. They're perfect for Fourier analysis. One way to Fourier analysis is to figure out the operator that describes d by dt and d2 dt squared, and then similarly figure out how to do that with d by dz. But really, the substitution affects that Fourier transform. So it's really not a preposterous idea. Okay? Now, it doesn't get us exactly what we had before, but the differences are instructive and useful. Okay? So if I substitute this in, I get those three terms. If I multiply by or divide through by the exponential, I have an equality that holds for all z and t. And so that means that this algebraic equation is the solution to the differential equation. I have solved the differential equation. The fact that I have an algebraic term there, the algebraic equation, means that I have solved the differential equation with this solution. Okay? That's what I mean when I say solve the differential equation. Satisfying that equality for all t and z that are the dependent variables in the equation. Okay? It also is just an indication of Fourier transforming, turning the differential equation into each term into an algebraic term. Okay? The equation is independent of the strength of the field, which is another indication of its linearity. If this were a nonlinear equation, the solution would be dependent on the amount of field that I had. But that's not the case, because these E naughts cancel each other out. This term I had before, this term I had before. This term is new, and I now have the square root of minus 1 that's slithered into my problem. Okay? So now I have a complex argument, or a complex number floating around. So before we solved for what this degree of freedom was, k, in terms of the frequency that I was operating at and the material constants. And now I have the same relationship, the same dispersion relationship, but it's complex. Square root of minus 1 complex. So that implies that wave vector, that wavelength that I had before, that 2 pi over the wavelength term, the k term, the propagation constant term, the degree of freedom term, that now has a k in it. It's complex. Okay? So I'm going to rewrite this just a little bit to make it a little more malleable. So I'm going to reduce down to an equation that I had before, plus an additional term that's well identified. If I ignored that, or if I let sigma go to 0, that's exactly the dispersion relationship that I had before. That's exactly the relationship between k, omega, and the speed of light that I had before. That's c is equal to lambda nu. Or I think as you liked it, c is equal to lambda f. Okay? So that relates the wavelength to the frequency to the speed of light in that material. Just what we had before. But now we have this additional term where because of sigma, because of the loss, that relationship gets a little bit more complicated. So I'm going to do a couple of different limits. If sigma is small, not 0, but if it's small, and what I mean by that is if this term is small relative to 1, let's say a tenth of that, or a hundredth of that, or some reasonable relationship that satisfies our engineering intuition, or the requirements of precision. If that's a little bit less than that, or significantly less than that, then I can do a Taylor series expansion. And I can write that. So I take the square root of both sides. Get that there. I have the square root of this, or this term raised to the 1/2 power. And 1 plus epsilon to the 1/2 is 1 plus epsilon over 2. Oh, I shouldn't say it that way. 1 plus a small number, theta, quantity to the 1/2, is equal to 1 plus that small number, theta, over 2. Okay? So that's just a Taylor series expansion. And now I can say k prime, or now I can say k is equal to k prime plus I k double prime. It's a very common notation that says that my propagation constant k is separated out into a real part and an imaginary part. Okay. And the real part, k prime, is exactly what I had before. So the real part of k prime in that limit where sigma is small losses, is that I still have wavelengths, I still have frequencies, it's still a nicely propagating wave. Okay? Nothing major happens. Okay? But there is an imaginary part, and I got to figure out what to do with that. And this is only approximate because I'm in a limit. The units of this are kind of interesting. I've got an impedance here, and I've got an impedance there. But this impedance is actually per meter. The units of this still 1 over a characteristic length L sub A. If I substitute this back into my guess here, I can start to see what's going on. my complex K breaks apart into a real part, which is exactly what we had before. I'm sorry, an imaginary part here and a real part here. The imaginary part is exactly what we had before, and the real part, thank you, is this. And if I sketch this, these two terms here, I have a decaying exponential, but because of this requirement here, I've greatly exaggerated the exponential decay. So typically for these kinds of systems, you'll go hundreds of wavelengths before you see an appreciable drop due to this real exponential. Okay. So I think we called this an underdamped solution. Is that a term that you guys have used before? Damped exponential. Slowly damped exponential. And now we can now interpret what I mean by this. LA, which is I call the absorption length, gives you the 1 over E point of the decay of the field. So what's the value for 1 over E? 37% or something like that. So when 1 volt per meter comes in and I have 0.37, that's distance there, where this guy goes to a -1. Z equals LA. Gives me that distance is that interpretation. Okay. And that's a very, very common case. That would be the case of a fish tank that you probably didn't clean in the last couple of days. Okay? Or if you don't like animals, even fish, you have an empty tank or an empty glass of water and you drop just a drop of ink in it, or food coloring, or a drop of Diet Coke in it, or something amber colored, or something like that. And now you have a little bit of a cloudiness, and not as much light goes through that glass, not as much light goes through the fish tank. Okay? So that's just an absorbing case. Just your energy is just getting absorbed a little bit. Okay? Small perturbation on what we had before. Now, going back to this term here, I didn't neglect this term altogether. I kept part of that information, but I just expanded it as a Taylor series. If sigma is really big, like I am propagating into a metal, for example, then this term might be large relative to 1. So if this term was 1/10 of that, we were at the boundary of the sigma equals small limit. Now if this guy is 10 times what 1 is in magnitude, we're sort of on the other side of that criteria. So if sigma is large, neglect the 1, and I have k is equal to the square root of mu epsilon times omega times the square root of minus I sigma over epsilon omega. Okay, pretty simple algebra, right? But we have to remember one of those silly little fun facts from high school mathematics. We have to figure out what to do about that square root of I. Right? So we get there by Euler's relationship. And I see that if I do e to the I pi over 2, cosine of 90 degrees is 0, sine of 90 degrees is 1, so I can write I as a complex exponential. And now I have the square root of I, which is equal to the square root of e to the I pi over 2, which is equal to e to the I pi over 4, which is equal to the cosine of pi over 4 plus I sine of pi over 4. Pi over 2 is 90 degrees, so pi over 4 is 45 degrees. I can almost remember how to do that. I'm remembering root 2's. And so I have that situation. So I still have this minus sign here that I'm going to take the square root of. So that gives me another I in front of that. Gives me another I in front of that. So I have an I, and then I have a minus 1 there. So I still have a little bit of that left over, but at least I can start down this path. Mu times the square root of omega times the square root of mu epsilon. I have an I. From that square root of minus 1, I have a square root of sigma over omega epsilon. And then I have a 1 plus I over the square root of 2 from that guy there. Lump all this stuff together. And I have a sigma in the numerator. I have a mu in the numerator. I have an omega in the numerator. My epsilon cancels, and I've got a square root of 2 sitting there. And then I times 1, I times I is a I minus 1 sitting there. So remember, I still have a k is equal to k prime plus ik double prime. It's still a complex k. Last time I looked at k double prime, it had units of 1 over length. It has to have units of 1 over length here too, just because of what it's doing in the exponent. And I'm going to call this 1 over delta. And this is called the skin depth. And delta is short. Short relative to, well, it's kind of an interesting point here, isn't it? If I substitute these back into the exponential, I still get the same kind of behavior, where this is now a skin depth instead of an absorption depth, so it's much, much, much faster. But what's really kind of interesting to me is if I now look at k prime and k double prime, they're the same. They're the same. So if I use the word underdamped solution here, do you remember what I should use here? Critically damped. So it's not overdamped. Or it might be by some 2 pi or something floating around in there. But what's really interesting is, because of the way this works, regardless of frequencies, regardless of sigmas, as long as sigma beats out this one, regardless of the frequency, the wavelength adjusts so that the K prime and the K double prime are the same. And I have some semblance of critical damping floating going on in there. There's also a flip in the minus sign here. And what that means is that what that means is the plus goes to a minus and the minus goes to a plus. And remember that that's indicative of the direction of propagation. So when this wave hits the shiny metal surface, it wants to turn around and get the heck out of Dodge. Okay, so that's what's floating on with this minus sign here. Okay. So skin depths for metals are calculated by this, and it's not a bad thing to sort of, if you're working with metals, to kind of know what your skin depth is. That's basically how far into the surface of the metal the wave propagates. And it doesn't really even propagate. It just sort of surfs in there. We actually call it an evanescent wave. Okay, when I have this quickly damped exponential that dominates the behavior much more than the oscillation, then it's an evanescent wave, non-propagating evanescent wave. Okay. Yeah.
Kind of unrelated question, slightly, just quickly. So on skin depth, interesting question is, so I've heard that you need to make sure you have enough skin depths to not lose much power or current.
Yeah, that's a really good point.
But then again, at lower frequencies, they say that if your trace thickness is very small compared to the skin depth, then you're okay.
So the question has to do in a practical engineering board layout. What does a skin depth mean with respect to like a requirement on a trace thickness or a metal film thickness? Let me sketch it, and we'll see exactly what we're doing. So if I have a boundary, and we're going to do this in better detail next time, but maybe this is more practical than what we'll do next time, so it's worth looking at. And I'm going to have two situations. I'm going to have a decaying exponential that looks like this, and a trace thickness that's this wide across metal. Okay? So if this is about my skin depth here, you can see that I've gone 5 skin depths. And the amount of field that I see here is down e to the minus 5, which is a fairly aggressive function. So the value of your volts per meter is much smaller. It's been driven. Now, supposing instead I have a trace thickness that's only here. What that means is that there's still a significant amount of field that's hanging out there. Okay? And what can happen is I can continue to grow my field. My field can just propagate, or I think it's sometimes called tunneling through the barrier. Okay? So the bottom line is, if you want a trace to really act as a trace, like a conductor, you want to make it many times its skin depth, okay, so that you damp your field tremendously. What time is it? I have half an hour. I may look at this towards the end of class in a little bit different way, or it may have to spill over to next class. We'll take a look. Depends on how long-winded I am on my next little section. Okay?
Yes.
But let's come back to that skin depth. And what it might mean to a real trace design. Does that answer the question pretty well?
Yes.
I think
I'm working
so.
in the mid-megahertz region right now, so I have to
Slow.
make a decision.
So very slow. So again, this is exactly the engineering part of it, right? What's your conductivity for gold or copper? Oh, by the way, what's your conductivity for evaporated gold and copper in your particular setup, right? Because if you evaporate it, it's not going to be quite as dense. It's going to have a slightly different conductivity. So you sort of have to either establish that or ballpark it or downgrade your if you switch vendors, maybe you switch sigmas on those things. Practical stuff, right? There's no dielectrics here, so it's just it's a metal. So there's mu if it's a non-magnetic metal. That's just mu naught. If it's iron or something like that, you've got to figure out what you're going to do with that mu. Okay, and then you've got your frequency. You said mid megahertz. And is that like 100 meg?
No, below that.
Below that. So that's a small number.
Yes.
And that means your skin depth is going to be fairly small. So you get away with
Yes.
The other interesting thing that I see out of this equation is taking it to a very different limit. And you remember this k is the wavelength, and the wavelength is sort of the ruler that a plane wave carries around with it. It becomes a measure of the uncertainty of the size of where the energy is, if you want to, you can think of it that way, or if you're doing, say, photolithography for a chip, you can't really focus. You can't have features that are finer, too much smaller than your wavelength. You can't focus light to a point that's smaller than your wavelength, right? And that's sort of this picture here. So if you're working with green light, 500 nanometers. You really can't image something that's smaller than 500 nanometers very reliably in a typical optical microscope. So if you're working with the sodium D line, the green line, you're seeing things that are half a micron at best. So whatever biological samples, your cells, your what have you, better be bigger than that in order to be able to see it. And but here, take a look at this. If I replace my glass lenses in my microscope with metal lenses, then what I've done is I've tremendously improved my resolution. So I'm no longer bound by the 500 nanometers. I'm now bound by the 10 nanometers of my skin depth of my metal. So I've gained a factor of 50 in resolution. The price I've paid is that my field strength is down by that much. My field strength goes down tremendously. But if I have the signal to noise, I can trade that signal to noise. If I have enough power, for example, if I have enough field strength, way above my detectivity, then in fact, yes, I absolutely can play this game in certain ways to trade off power for resolution. Okay? And that's the nature behind some of the scanning tunneling microscopy, or more precisely, the near-field scanning optical microscopy that allows you to image things with a wavelength that's much smaller than the wavelength. Okay? And it's exactly this critical damping thing. But I guess I get a kick out of thinking about the final lens in your microscope being a small blob of solder that you tunnel through to image what's underneath it. I've always wanted to build that microscope. Don't think it should be terribly difficult in today's world. So maybe I'll get around to it. Problem is it costs money, and it's kind of a tricky thing to get funded on, because it'll work, but, oh well. Okay, so to summarize, the solution for both of these cases is this. And this term gives you the old propagation term. And the other term gives you, and notice the flipping of the signs. Well, it will flip the signs. This is the damped exponential term. Okay. The analogy that I started the class with when I was talking about the material relationships, capacitor, inductor, and resistor. Before we had just the capacitive term and the inductive term, and I had a nice oscillation that's similar to an LC solution, a solution to an LC circuit. If I now add in the resistors, say even just the impedance of the wires, the resistance of the wires, I have a third term, and my nice sinusoids now in my LC circuit now become damped exponentials in my LRC circuit. And that's exactly what I did here. So, LC circuits going to LRC circuits. Okay. Now, all is almost okay. I did two cases. I said if this is small, and I said if this is big. Now, your sigmas, epsilons, and omegas will vary. Well, your omegas alone, for example, will vary from 1 to 100 gigahertz. 1 to 100 terahertz, if you really want to think of it that way. That's 12, 13, 14 orders of magnitude. You have to be pretty unlucky to be working at exactly that wavelength that's where this guy is about equal to that guy. Right? So just to put it in context, if the only variable that I have in this is frequency, from DC to daylight, I'm looking for a factor of 10 higher or lower. So I don't have much, the odds are pretty much in my favor. But let's look at that case anyway. Okay? If I take this equation here and I substitute it into my wave equation here, I'll get a slightly different form for this solution. So take this solution, sub it into the wave equation, and I get this result here. Multiply out this guy here. I think, is this a positive sign here? I think it is. So I have a real part on this side and a real part on this side. I have an imaginary part on this side and an imaginary part on this side. You'll see that depending on whether I'm overdamped or underdamped, this guy comes into play in that propagation term. And then I have 2 2 k prime k double prime mu sigma omega. If I take the imaginary part over the real part, it sounds reasonable if I'm looking at some sort of phase issues in a complex quantity. Imaginary part over the real part, the tangent. Sigma over omega epsilon, which we've seen before. But this is the standard the derivation to describe the loss tangent, imaginary over the real part. Okay. So generally speaking, in the RF microwave region, you describe the loss tangent as a way of saying how much loss or not you have in your system. But it's not very different from what I just did in taking my limits here to here. Okay, good. Any questions about that? All right, let's go and look at your problem a little bit more carefully. Okay? And what I'll do well, let's go back to your trace problem. Let's go back to your, and just really abstract it and just say, what do I know about charges and fields inside a conductor? Or better yet, what does Maxwell's equations tell me about charges and fields inside of a conductor? So what I'm thinking about is I'm thinking about a blob of gold. Okay, in my desk drawer somewhere, I've got a little 1 cubic centimeter of gold that we were using a long time ago for evaporation. I shoved it in the back of it, and every once in a while, when I want to feel rich, I pull it out and take a look at it, even though it's not that, it's bright and shiny, but it's not that valuable. But anyway, and if I ever need to evaporate gold again, I have it. But what I'm thinking about is, supposing I have that piece of gold, a very, very good conductor, by the way, and used all over the place on printed circuit boards. And I want to think in terms of what happens if I somehow magically take a charge and try to shove it in the middle of that gold. Or maybe a couple of charges and shove it in the middle of that gold. What's going to happen? So if I've got 2 charges and they're shoved in the middle of the gold, there's going to be a repulsion force on it, right? And they can move because gold is a good conductor that enables the movement of this charge. And there's no love between these 2 electrons, so they're going to try and they're going to repel each other. They're going to try and get as far away from each other as possible, right? That's just intuitive. And so now they're going to be sitting on the edges of this gold blob. And if one shifts over and gets a little bit closer, the other one's going to move. They're going to stop moving when they run out of conductivity, right? They're going to stop moving when they run out of conductivity. And that's exactly at the surface of the gold blob. Okay? So think about that for a second. And then, while I entertain you with some mathematics. Okay? So let's go back to one of my favorite equations. This is not del B, the divergence of B equals 0. That's a joke. Everyone's cracking up, I can tell. So there's my curl of H is equal to del D del T plus J. And remember, we always like to take second derivatives of Maxwell's equations. And we've already done the curl of this, or at least I suggested you do the curl of this to derive a wave equation for H. So I'm going to do the del dot of this. And we sort of did this before. This guy here is now 0. The right-hand side is del by del T of the divergence of D plus the divergence of J. And I have the divergence of D is equal to rho. And remember, I've combined these guys together in the past to derive the continuity equation, sometimes called Maxwell's fifth equation, for the conservation of charge. Charge can't be created or destroyed, it can just be shoved around, moved around. And I've got this guy here. And this was the continuity equation that we've derived before. Conservation of charge as before. But now let's try our other constitutive relationship. J is equal to sigma times E. Okay? So let's keep working on this guy here and put J is equal to sigma times E in there. So then if I substitute that in, I get a sigma times del dot E is equal to minus del rho del T. But the divergence of E, as I saw before, was rho upon epsilon. Same thing as this guy here. Just almost undoing what I did before. And the right-hand side of that is minus del rho del T. And let me just rewrite that into a slightly neater form. What I have is I have an ordinary differential equation for rho, the rate of change of rho, d rho dt, and that's equal to minus sigma over epsilon times rho. Well, I don't know about you, but this is about as cake a differential equation as we can solve. Ordinary first-order differential equation with constant coefficients. It's an exponential, right? So it looks like if I have this good conductor and I mess around with the mathematics and the material relationships of this, that what I have for the charge behavior inside of this metal is a solution that looks like that. And epsilon is a transcendental function, so the argument of that transcendental function has to be unitless, dimensionless. So this is going to equal rho naught times e to the minus t over some time constant, which is sometimes referred to as the Debye time constant. And this time constant is equal to epsilon over sigma. So as sigma goes to infinity, my conductivity gets very, very high. I'm in a superconducting state, perfect conducting state. My tau d goes to 0. Okay. So now put that back in the context of my gold blob that's in the back of my desk. Better start locking my office door. Really, it's not that big a piece of gold. Trust me. But that if I now have those electrons inside of there, this very silly and simple approach tells me just how fast those electrons want to get out of that center of the gold. The higher the conductivity, the faster they're going to flee to the edges of the gold. And so it's kind of interesting. Let me just draw a little table for you. And what I want to do is I'll do a good insulator like glass, and I'll do a semiconductor like silicon, and I'll do not gold but silver, a good conductor. And for silver, if you look up what sigma is and you look up what epsilon is, you get about 3 attoseconds. 3 times 10 to the 18 seconds. Very, very fast. The fastest laser pulses right now are about 100 attoseconds. A Herculean result. It'll get shorter because there's a whole new class of physics. So someday, probably in a decade or so, maybe half of a decade, probably a decade, 8 years or so, we'll have lasers that are able to probe the electrodynamics of the movement of the electrons inside your leads, for your traces. Silicon is about 90 femtoseconds, which is a heck of a lot faster than your 50 meg, right? But 90 femtoseconds, those type of delta functions have been around for a couple decades now. So not too hard to get to on that. And then the tau sub d. Oh, so just so you know, there's 4 orders of magnitude difference there, right? Femtoseconds, 10 to the minus 15, 10 to the minus 18. That's 4 orders of magnitude. That's just going from silicon to a metal. You get 4 orders of magnitude change. You go to glass, your good insulator, and this is about 3.5 times 10 to the positive 6. So that's 24 orders of magnitude between this guy and this guy. Right? There are very few material constants that vary over 24 orders of magnitude. 24 orders of magnitude. That's a lot. I mean, that's for a material constant. Nobody's impressed. All right. How long is a million seconds or 3 million seconds? Believe it or not, it's even longer than one of my lectures. That's 40.5 days. Okay? So if I take glass, and think about this, right? I should be able to concoct an experiment where I can liberate an electron inside of a glass plate. I mean, I should be able to figure out a way to embed some sort of ion trap inside my amorphous glass structure, and then pound it with a laser to free the charge from it. Got to try to do that without breaking the glass, but I should be able to figure that out, shaking it enough. Well, now this electron will move to the surface in about a month and 10 days. Okay? It will get there. It will get there. It will migrate to the surface. But it'll just take a lot longer than if it was made out of silicon instead of silicon dioxide. Okay? So the moral of this is, as long as I have any kind of conductivity in my system, and I mean this in the literal sense of conductivity, that electrons can flow, then all my charge is going to pile up on the surface of my material. Okay? And if you remember our boundary conditions, where the change in the electric field and the change in the magnetic field mattered because of the charge or the moving charge on the surface, well, we now know that that's where all the charge is basically going to be. Okay? So you could go back and you can take a look at the electric fields inside your traces and think in terms of the charges that are wiggling around in there and how far they might get to. Will they get to the edge of the trace in that time constant? Okay. Well, this is an important digression to point out where the charge is, because next time what we're going to do is we're going to take our plane wave solutions and we're going to bounce them off of walls. Okay. We're going to take a plane wave solution and we're going to bounce it off of a shiny metal surface. I'm going to describe it as a shiny metal surface. I'm giving you a big old hint about what's going to happen. It's going to turn around and come right back on us. It's not going to propagate very far into the shiny metal surface. We know that because of our skin depth calculations that we did. High conductivities, it just doesn't go very far. And we also know when we're going to solve that the boundary conditions we're going to have to think in terms of charge and moving charge on that surface, but not necessarily inside that surface. Okay? Then we're going to do a perfect block of glass at normal incidence. Then we're going to do a metal at oblique. I'd probably do the metal at oblique incidence, and then we'll do the glass at perfect incidence. Okay? So we'll take our plane wave and we'll bounce them off at surfaces. And with that, I'll quit a little bit early for the night. Thanks, guys.